Welcome all first PG students to my class. We are starting with the unit 4 of elementary inorganic chemistry. The name of this chapter is given as chemistry of transition and inner transition elements. Before coming to the contents of the chapter, we have to refresh some topics which you have already been studied in your lower classes. I mean your higher secondary and UG classes. The term on the board you can see that electrode potential. What is electrode potential? It is the potential established at the interface of a solid and liquid when a metal rod is dipped in its own salt solution is known as electrode potential. Simply we are writing as E0. This E0 should not be confused with EMF of a cell. We are now discussing about the electrode potential of a single electrode. After connecting such two electrodes, we can construct a galvanic cell, and electrode potential difference of that two electrodes is termed as EMF. That is a different concept. Now we have to see the electrode potential of a single electrode. Definition I have already mentioned. The process can be explained like this. Suppose a metal rod dipped in its own salt solution. Such conditions you have heard many times in your UG classes. Example, when zinc rod is dipped in zinc sulfate solution and copper rod is dipped in copper sulfate solution. That I mean, when a metal rod is dipped in its own salt solution, metal rod and salt solution, conventionally we are expecting that a metal rod is made up of large number of metal atoms and solution contain metal ions. Example, when copper rod is dipped in copper sulfate solution, this rod contains copper atoms and solution contains Cu2 plus ions. Here in this solution, two kinds of things can be happen. First possibility is the dissolution of metal atoms from the electrode to the solution. Dissolution of metal atoms in the metal rod to the dissolved in solution as Mn plus. Equation can be written like this: M gives Mn plus plus n electron. During this oxidation process, n electrons are released which remain on the electrode and ion only enter the solution. When this process continues for some time, charge separation can be established at the interface of the solid and liquid. How it happened? Initially we have a neutral electrolytic solution to which we have added electrode or metal rod. When this metal ion dissolved to the solution, when this metal electrode dissolved to the solution as metal ion, concentration of positively charged metal ion increases in solution and solution become positively charged in total. During the course of this oxidation, electrons are released which get accumulated on the electrode. For every oxidation, n electrons are released. In the case of copper, Cu gives Cu2 plus 2 electron. For the dissolution of every copper from the copper electrode, 2 electrons are deposited on the electrode. Thus, electrode become negatively charged with time. Then solution is positive and metal rod is negatively charged. So, at the interface means the area where solid and liquid come in contact with each other. In that interface, a potential difference is established due to this charge separation. That potential is called electrode potential of that electrode. Again consider metal rod is dipped in its unsolved solution. Another possibility to happen is that the Mn plus ions present in solution can accept electron from the electrode and deposit here as the metal atom. Mn plus in solution accept n electrons from the electrode and deposit on the electrode as the metal. When this process proceeds, solution becomes negatively charged. For example, in copper sulfate, each copper sulfate molecule consists of Cu2 plus and SO4 minus. Out of these two ions, copper 2 plus alone goes to the electrode. SO4 remains in the solution, which makes the solution negatively charged. For every metal ion reaching the electrode, that electrode needs to give n electrons. By giving the electron, that rod become electron deficient and become positively charged. In this condition, electrode is positive and solution is negative. Under this condition also, we can expect electrode potential or potential at the interface, which is known as electrode potential in this case. So, two kinds of reactions can happen. Sometimes metal atoms tend to lose electron through oxidation. Such potential is called oxidation potential. Sometimes metal ions in solution have a tendency to accept electrons and get reduced. That process is called reduction potential. So, normally we can have two types of potentials, oxidation potential and reduction potential. The value of reduction potentials or oxidation potentials of many electrodes you have heard in your previous classes. Example, E0, Cu2 plus bar Cu is plus 0.34 volt, E0 Zn2 plus bar Zn gives minus 0.76 volt. These values are all you know. Oxidation potential, reduction potential. One thing we have to remember here is that even if we have two kinds of potentials with us, in general convention, we are always using reduction potential as the electrode potential to avoid confusions and complications. So, for any purpose, when you are taking electrode potential, that is reduction potential. If you need to get oxidation potential, no doubt at all, you have to make the sign opposite. I mean, reduction potential of copper is plus 0.34. Then oxidation potential is minus 0.34. Reduction potential of zinc is minus 0.76. That means oxidation potential is plus 0.76. We need just the reversal of the sign. Magnitude is same for both oxidation and reduction potentials. These we have seen so far is electrode potential. Now we come to standard electrode potential. What is standard electrode potential? That is the potential measured at standard conditions. What are standard conditions? Standard condition means pressure 1 atm, concentration of metal ion should be 1 molar, and temperature should be 298 Kelvin. If the three conditions have satisfied by a particular electrode system, the potential of that electrode system is called standard electrode potential. We have already used many electrode potentials for doing problems and for calculating EMF and for many other purposes. At that all conditions we have used standard electrode potentials, not electrode potentials, standard electrode potentials. Here in this section you have learned about SHE. What is SHE? Standard hydrogen electrode, which is a primary reference electrode using which we can calculate the standard electrode potential of other electrodes. I don't want to detail here, and the setup and maintenance of SHE is very difficult because it involves a gaseous reactant hydrogen. So for convenience, this primary reference can be substituted by some other secondary references such as calomel electrode. That also you have studied in your UG classes. If you have any doubt about it, you can refer that textbooks. Now we are coming to electrochemical series. What is electrochemical series? For each and every element, they have their own standard reduction potentials, which we are generally calling standard electrode potentials. When these species may be metal or non-metal, when these species are arranged in the increasing or decreasing order of standard electrode potential, that series is known as electrochemical series. Arrangement of various species available with us in the increasing or decreasing order of their standard electrode potential is known as electrochemical series. And this series is expected to have many applications in electrochemistry for the prediction, for the comparison, and for many other purposes. This series is widely used for. So we have to see in brief. This is electrochemical series. Here you can see various species: lithium, potassium, calcium, sodium, magnesium, aluminum, zinc, iron, cadmium, lead, copper, and so on. And in the middle you can see hydrogen here, SHE, and below hydrogen you have bromine, tin, copper, silver, mercury, and lastly you have fluorine. In this series we have represented the species in the increasing order of reduction potential, which I mean a species with the lowest reduction potential is placed at the top, and the species having highest reduction potential at the bottom. Minus 3.05 at the top and plus 2.87 at the bottom. What applications you have studied about it? First application is that selection of reducing agent and oxidizing agent. Selection of reducing agent and oxidizing agent. And first, you have lithium. Lithium have low reduction potential. Reduction potential means tendency to gain electron. Tendency to gain electron is -3. That means lithium does not have any tendency to gain electron. Then automatically it should have tendency to lose electron, because we have already declared that when reduction potential is negative, oxidation potential should be positive, and vice versa also be true. So for lithium, it has no tendency to accept electron, so its reduction potential is negative. But at the same time, lithium should have the tendency to donate electron. You can see this equation here. Li plus 1 electron gives Li. Lithium ion 1 electron വാങ്ങാനുള്ള സാധ്യത -3 ആണ്. So you have to reverse the equation. Li gives Li plus 1 electron is +3. This is oxidation potential. This is reduction potential. So being reduction potential is highly negative, then itself it is clear that oxidation potential will be very high. So lithium have a greater tendency to donate electron. As the standard electrode potential or reduction potential gradually increases, tendency to gain electron gradually increases, or tendency to donate electron gradually decreases. Lithium shows highest tendency to donate electron, and as we move down the series, that tendency of donation of electron will decrease. Now one question you have is that whether this lithium is oxidizing agent or reducing agent. Whether this lithium is oxidizing agent or reducing agent. Here lithium is expected to be a good electron donor, not acceptor. Electron donors are good reducing agents. Electron donors are good reducing agents. So lithium is a reducing agent, strong reducing agent, because of its higher tendency to, better tendency to, increased tendency to donate electrons. As we move down the series, there is a decrease in the tendency of donation of electrons. That means capability to act as reducing agent also decreases. So the most powerful reducing agent is lithium at the top, but while stating that, you have to say that lithium is the powerful reducing agent, that is okay, but in aqueous solution. In the absence of water, lithium may not be the good reducing agent. And we are coming down and down, and finally we will reach where we will get fluorine. Look into the value of fluorine. Reduction potential of fluorine is highly positive, that is plus 2.87. What it means? Which actually mean fluorine has a greater tendency to accept electron. Fluorine has a greater tendency to accept electron. F plus 1 electron gives F plus 1 electron gives F minus. That has the value of 2.87 positive. So it is a good electron acceptor. That is a good oxidizing agent. So tendency to act as reducing agent decreases, while that of oxidizing agent increases. And finally we declaring lithium as the strongest reducing agent and fluorine as the strongest oxidizing agent in aqueous solution. That is the first application. The second application is that reactivity of metals can be combined. Reactivity of metals can be combined. from the series which is a better metal or good metal or a strong metal, or which is the metal having highest tendency to donate electron. In your lower classes, I think in 7th or 6th standard itself, you have studied what is a metal. Metal is an elemental species or element having the tendency to donate electron. Any element having the tendency to donate electron is called metal. In this diagram, who will contribute metal, who will donate metal in better? Those who have the lowest tendency to accept electron should donate electron fastly. Who is that one? The species having lowest reduction potential. Species having lowest reduction potential. So lithium is the highly reactive metal. As we move down the series, reduction potential slowly increases. Tendency to gain electron slowly increases, then metallic character decreases. So we can say that reactivity of metal decreases down the group. So lithium is the highly reactive metal, potassium is less reactive, but generally we can say that this region is a region of high reactivity. This region is reactivity of up to aluminum. Third application is displacement reaction. Displacement reaction. When zinc powder is added to CuSO4 solution, you will get ZnSO4 plus Cu. What actually happens is that blue colored copper sulfate become white colored or colorless. The real reaction happens is that more reactive zinc displaces less reactive copper from the salt solution and becomes zinc sulfate. This kind of displacement is possible in electrochemical reactions, and the product or outcome of that kind of reactions can be predicted using electrochemical series. See here, where is the position of zinc? Here you have zinc, and here you have copper. In the previous application, we have told that as we mount down the series, reactivity of the metal decreases. So zinc is more reactive than copper. So any metal having higher metallic character or higher reactivity can displace less reactive metal. A simplest form we can say that any metal at the top of the series can displace metal at the bottom from their salt solution. Aluminum can displace zinc. Aluminum can displace silver. Aluminum can displace copper. Copper cannot displace aluminum. Copper cannot displace calcium. Copper cannot displace sodium. These are the third applications. Now, the same thing can be used to predict the displacement of hydrogen from mineral acids. For example, displacement of hydrogen from mineral acids. That is the fourth application. See, when sodium is added to hydrochloric acid, the product will be NaCl plus H2. This is a character of metal, or this is a character of hydrogen. Metal can displace out hydrogen acids. Mineral acids, hydrogen from mineral acids can be displaced by metals. So sodium displaced hydrogen. Common ions are Cl minus, here also Cl minus, that can be cancelled. Actually reaction is Na plus 2H plus gives 2Na plus H2. Why it happen? In electrochemical series, sodium is at the top and hydrogen at the here is hydrogen at the bottom. So the metal at the top can displace hydrogen. When magnesium is added to HCl, that also displaces hydrogen. Aluminum can also displace hydrogen. Zinc can also displace hydrogen. Iron can also displace hydrogen. This is possible for these metals. But when copper is added to acid, there will be no displacement because copper is below the hydrogen. Mercury cannot displace, silver cannot displace, gold cannot displace. So metal at the top of the hydrogen can displace hydrogen, but any metal from the bottom part of hydrogen cannot displace hydrogen from the mineral acids. And also one more application we have in chemical series is that the selection of cathode and anode in electrochemical cell. What actually a cathode is? The electrode at which reduction takes place is called cathode, and the electrode at which oxidation takes place is called anode. In cathode, reduction takes place, and in anode, oxidation. Reduction means tendency to gain electron. Oxidation means tendency to lose electron. So, in an electrochemical cell, element at the bottom. In Daniel cell, we have zinc and copper electrodes. Copper acts as cathode and zinc acts as anode. Zinc is here, copper is here. So, in an electrochemical cell, element at the top can act as anode and bottom can act as cathode. That is the selection of cathode and anode. These are all about the applications of electrochemical series. It is vast and wide, but we have discussed in a brief mode. Now that part is completed. Now you have to see two processes, disproportionation and comproportionation. Disproportionation, you have heard it very clearly. I don't know about the comproportionation. Anyway, disproportionation is familiar to you. When an ion is unstable in a particular oxidation state, it undergoes self-oxidation and reduction simultaneously to neighboring oxidation states. That is called disproportionation. Cu plus seems to be unstable. So it undergo oxidation and reduction simultaneously to Cu2 plus and Cu. This process is called disproportionation. Now we have to check whether it is thermodynamically feasible or not. For doing it, you have to see some equations in electrochemistry that also you have studied in previous classes and you have seen in the previous slide. E0 equal to 0.0591 by n into log Kc, where Kc is equilibrium constant, E0 is the standard EMF, delta G0 minus NF E0, and delta G0 is equal to minus 2.303 RT log Kc. These are three important relations in electrochemistry, especially in electrochemical part. From this equation, we can calculate the value of Kc if you have provided with E0 value. So, for this reaction, E0 Cu plus bar Cu and E0 Cu2 plus bar Cu plus both have been given. Oxidation half is considered to be anode and reduction half is considered to be cathode. What is EMF of the cell? EMF of the cell equal to E0 cathode minus E0 anode. Which is cathode? Cu plus bar Cu. Cu plus bar Cu. That is 0.52 minus, which is anode, Cu plus Cu2 plus. That has the value 0.16. So the answer is 0.36 volt. Since E0 is, that means standard EMF is positive, equilibrium constant should be greater than 1. We are putting this value in this equation, E0 equal to 0.0591 by n into log Kc. On solving, E0 substituted as 0.36, n is 1. 1 electron change is there. Then Kc will get as 1.3 into 10 raised to 6. For this, you have to take anti-log of some parameters. Then you will get 1.3 into 10 raised to 6 at 298 Kelvin. The value of Kc is, since equilibrium constant is very high, reaction will proceed in forward direction. That means Cu plus will automatically changes to Cu2 plus and Cu. So disproportionation is happening in this condition. No doubts at all on it. Now we have to see comproportionation. This is just the reversal of the disproportionation. In disproportionation, you have an unstable single oxidation state moving to two stable oxidation states nearby. But here in comproportionation, you have two unstable oxidation states of the same element come to a stable intermediate oxidation state of that element. For silver, Ag2 plus and Ag are unstable. They will undergo oxidation and reduction simultaneously to an intermediate Ag plus. So here Ag2 plus, Ag plus and Ag are three oxidation states. Both are unstable, so they will tend to come to intermediate oxidation number. Ag2 plus come to Ag plus, that is reduction. Ag come to Ag plus, that is oxidation. So both oxidation and reduction takes place simultaneously. This process is known as comproportionation, and this process, possibility of the process can also be checked as in the previous case. E0 is found to be 1.18. We have to substitute that in the previous equation, E0 equal to 0.0591 by n into log Kc. Then you will get Kc as 10 raised to 20, around 10 raised to 20, which is a big value or high value. This high value of equilibrium constant again indicate that the process will move in the forward direction or towards the right side. So Ag plus will be formed, and this comproportionation reaction is possible to greater extent. These are few basic things we should know to go forward in this chapter, where we have to see some new things which you may not have studied in the previous classes. So for getting into that topic, we have refreshed our pre-knowledge. Thank you, friends.